Today we have the pleasure to host Sebastian Kamann. So Sebastian did his PhD at ERP in Potsdam, then moved to Göttingen for a postdoc, and after that he moved for another postdoc at Liverpool. When he got this UK Research and Innovation Fellowship that then allowed him to become staff member at Liverpool John Moores University. So Sebastian is a very close collaborator of mine, of LAM, and collaborated also with some GRP people here for for a code that we wrote on PSF reconstruction about, especially about MUSE analysis, but not only, also about IFU, in general, IFU analysis for reconstruction of PSF stars in stellar crowded field. And is expert then of star cluster and stellar evolution. And then I'll leave him talk about his research now.
Thank you, Sylvia, for the kind introduction, and thank you for hosting me. Yeah, it's a pleasure to be speaking to you today about some of my recent research, which focused on young massive star clusters. And I was told that this is a very broad audience scientifically and also some instrumentation people. So I'll try and give a broad introduction on the topic and then show some of the research results that we obtained towards the end. So maybe just to give everyone a brief introduction of the objects that we're talking about here. So when we talk about star clusters in general, right, then I think there's some things that everyone agrees upon. That usually what we define as a star cluster is a gravitationally bound group of stars that form from the collards of giant molecular clouds, which then has some implications on the properties of the stars in such a cluster. For example, that they should have more or less the same age and that their chemical fingerprints should also be more or less identical. Now, on the second point, there's already some discussion about whether that's true, because we find that in some star clusters, actually, there's a surprising variety in chemistry. So star clusters are also almost free of gas and dark matter, which then tells us that their evolution is really dominated by the gravitational potential created by the stars themselves. And because these star clusters are so dense, the star clusters gravitationally interact quite often. So that's why we talk about these star clusters as collisional systems, because there's gravitational encounters on a very frequent basis between their member stars. And then the other important aspect, kind of defining the final fate of a star cluster, is the tidal forces of their host galaxies. And when we look at the Milky Way, then we typically think of two different types of star clusters. On the one hand, we have the low mass open clusters that are metal rich and young, typical ages of less than 1 gigayear, like the Pleiades that you see here and that we typically find in the galactic disk. And on the other side of the scale, we have the globular clusters, very massive clusters, usually more massive than about 10,000 solar masses, that are mostly metal poor, and really old. So those are some of the oldest objects that we can find in the Milky Way. And then, yeah, kind of how we think of these two classes is that the young star clusters we consider as the result of local star formation events that happened in the Milky Way disk. And because of their low masses, these clusters actually have very short lifetimes of the order of hundreds of millions of years, because they're quickly destroyed either by tidal forces of the Milky Way, interactions with gas cloud that they encounter in the galactic disk, or the evaporation by gravitational interactions and the relaxation of the clusters. And thanks to Gaia, we really now have a very complete picture of these low mass young star clusters in the disk. However, in my talk, I'll really focus on more massive star clusters. And the idea that we have in the Milky Way is that massive clusters equals globular clusters. These globular clusters, yeah, as I said before, they're typically considered to be some of the oldest objects for which we can get reliable ages in the Milky Way. And because of this, also their formation is still a bit unclear. For example, there's this what's called the multiple population puzzle, as I've already teased on my first slide, there are subtle differences in the abundances of certain elements that we still cannot explain. And another question related to these globular clusters is whether maybe they were the sites where the seeds of supermassive black holes formed. So there's an ongoing discussion about whether globular clusters hold intermediate mass black holes, kind of the progenitors of supermassive black holes. But also I won't focus a lot on these kind of objects today. But what I want to tell you today about is that basically our view of star clusters is actually a bit biased, I think, when we only look at the Milky Way. Because already if we look at our nearest neighbors, the Magellanic Clouds, then we find star clusters like this one, NGC 1419, and this one, NGC 1866, that look a lot like globular clusters and have masses of the order of 100,000 solar masses. So right in the ballpark where you expect globular clusters to be. But their ages are actually surprisingly young. So this cluster is about 1.5 billion years old. This cluster is 200 million years young. So these are really kind of a hybrid of, say, open clusters and globular clusters. And the Magellanic Clouds are not the exception here, because if we look at galaxies in the nearby universe, then we find these superstar clusters. So for example, what I've highlighted here is a star cluster in NGC 7252 with a mass in excess of 10 million solar masses and an age of 500 million years. And actually, this guy here is even more massive, I think 80 million solar masses. And the superstar clusters, they're typically associated in galaxies that have ongoing or recent merger events. Like you might still be able to see some of the shells around this galaxy that tell us about a recent accretion event. In order to explain these, we may have to ask ourselves the question of when do massive star clusters form? And what's consensus in the field that is that basically in order to form a massive cluster, a galaxy needs a high star formation rate, which is basically equivalent to having a high gas density. And if we look at the star formation rate density in the universe, then from this famous Madal plot, that we see that really the star formation rate, the cosmic star formation rate, peaked at around 10 billion years ago, so at around redshift 2. So it kind of makes sense that most of the massive clusters formed back then. But what is also true is that these conditions are still met in some galaxies that we find in the local universe, like the mergers I told you about on the previous slide, and also dwarf galaxies. And the Magellanic Clouds are really key objects here, because if we look at the star formation rate histories of the Magellanic Clouds, then what we see is that, for example, here we have the LMC. The LMC had an early burst in star formation, then a relative period of quiescence, and then it started together with the small Magellanic Cloud falling into the gravitational potential of the Milky Way. And here you can actually see these are estimated close passages of either the clouds or the clouds and the Milky Way. And you can see that whenever there was a close passage, that lead to enhanced star formation here. So we have in these clouds, we have enhanced recent star formation events that have been triggered by the interactions either between the clouds or between one cloud and the Milky Way. And this then also produced young massive clusters. And one very famous massive cluster in the Large Magellanic Cloud is R136, which we may well consider as kind of being a globular cluster in the making. So R136 is the central star cluster of the of the Tarantula Nebula, with a mass of the order of 100,000 solar masses. And what's also interesting about it is that it hosts basically the most massive stars that we know of. So I think the most recent estimate is that the most massive star in this cluster, R136A1, has a mass of about 300 solar masses. So these are quite massive objects. And then in that case, we might think of clusters like this one as gravitational wave factories. Because if we have these massive stars that are the likely progenitor of stellar mass black holes, and we have a lot of them on a very small volume, then it seems likely that after they basically collapse into stellar mass black holes, they might actually merge at some point. And actually, in a star cluster, you have dynamical processes that favor the dynamical formation of binary black holes. For example, at some point, these black holes will be the most massive objects in your cluster and mass aggregate to the center. And there they could build binary black holes dynamically. So the conditions for forming massive black holes in these star clusters are actually quite good. And from the observed LIGO gravitational wave events, we have some evidence for the dynamical formation of binary black holes. And these are especially the massive gravitational wave events. So one famous event was this GW 190521, which was two black holes of 85 and 66 solar masses forming a black hole with 142 solar masses. Now, these black hole masses are actually quite difficult to explain from single stellar evolution, because there's what's called the pair instability gap, which basically tells us that because of internal processes in the stars, stars shouldn't form black holes that are more massive than of the order of 70 solar masses. So then the idea would be that each of these black holes is already the product of a merger of two previous lower mass holes. And this is a process that's really only feasible in star clusters. So clusters really offer this possibility for hierarchical merging. But the big question is whether star clusters do actually retain their black holes. And this is a big uncertainty, because star clusters, if you look at them, they're very unsecure black hole holes because of their shallow gravitational potentials and short relaxation times. So if we look at the shallow gravitational potentials, they're a problem for two reasons. Because first, when you form a black hole from the collapse of a massive star, the black hole might receive what's called a natal kick. Because the supernova usually has some asymmetry, the black hole will receive a kick, and you can estimate the kick velocities by basically looking at known high mass X-ray binaries and check how far they are above or below the galactic plane. And if we do this, like in this paper by Atri et al., then you find that the kick velocities of most of the binary X-ray sources, the black hole X-ray sources, are in excess of 100 kilometers per second. And the typical velocity that you need to escape from a star cluster is around 50 kilometers per second. So even if these guys were formed in a star cluster, it's very unlikely that they would have been ejected shortly afterwards. Another problem is if you have a merger of two black holes, then the formed black hole will receive what's called a recoil kick. And these recoil kicks also typically have velocities of 100 kilometers per second or more. And there's one more problem, which is that if you think of the evolution of a star cluster where you have some massive stars, some low mass stars, at some point your massive stars might collapse into black holes. And then these black holes will mass aggregate to the center. And what the prediction was by Spitzer and others was that these black holes would form a kind of decoupled cluster with a short relaxation time. So that basically violent interactions between the black holes would kick them out quite rapidly. So that in the end, you would only be left with one binary black hole in the center of your cluster. This was referred to as the so-called Spitzer instability. And for this reason, it was believed until quite recently that, for example, globular clusters were considered to be completely devoid of black holes just because of this process. Nowadays, we know that the Spitzer instability is not as effective as we once thought, and we still expect healthy populations of the order of 100 black holes or more in some of the globular clusters. But coming back to young massive clusters, one other interesting aspect that we still don't really know about how black holes form is the interactions that, for example, a binary star goes through before forming a black hole. We know that most of the massive stars live in binaries that will actually interact at some point of their lifetimes. And these binary interaction phases are actually very poorly understood. So here's one sketch of how a black hole might form. So you have a binary of two massive stars. At some point, the most massive star will evolve off the main sequence and will trigger some sort of mass transfer. Then you'll have a stripped star in a binary with a more massive main sequence star now. Then this stripped star might collapse into a black hole. Then the black hole might accrete from its companion. So you'll have an X-ray binary. At some point, your companion will start expanding. You could have a common envelope phase. And then again, a stripped star. And at some point, you'll have your binary black hole. So you see there's at least two interaction phases here. And both mass transfer and especially common envelope phases are very poorly understood. So in order to enhance our understanding of how black holes form and how black hole binaries especially form, we also need more observational constraints on these rare but important evolutionary phases. And young massive star clusters really offer us a controlled environment here, because for all these binaries that we would find in such a star cluster, we would know the ages and the metallicities of the stars. And then, because we usually expect that, for example, this mass transfer would happen right after a star leaves the main sequence, and we know, because we know the turn of masses, we can then also know the progenitor masses of these. So that's one of the reasons why I think it's interesting to study these young massive star clusters. Another is that they actually, if you look at them, they have surprisingly complex color magnitude diagrams. So this is one star cluster in the large Magellanic Cloud, NGC 1846. It's about 1.5 billion years old. And if you look closely here, then you see that at the main sequence turnoff here shows quite a large spread in color, which is much larger than the photometric uncertainties of this HST observation. And if we go to younger clusters, then we find that, like, for example, NGC 1866, the 200 million year old example I showed on one of the first slides, they actually not only have this extended main sequence turnoff here, but if you go further down the main sequence, you see that also the main sequence is split. So we have a blue and a red main sequence. Now, when people first found these, they were very excited because they thought, well, this could be evidence for age spreads, because you could, for example, fit two isochrones here and then say that the blue main sequence would correspond to a younger population that formed basically after the main red sequence population here had already been in place. But there's a problem with this interpretation, because the age spreads that were inferred from this, from basically fitting isochrones to the two sequences here, they were found to be a strong function of cluster age. So here you have the age spread that was inferred from these two main sequences, and here you have the ages of the clusters. And it seems unlikely that basically a cluster with 100 million year old would only form stars over about 25 million years, while a cluster that formed 1 billion years ago would basically have formed stars over around 200 million years. And instead, then, what was found was that a stellar evolution effect is a more likely explanation for this, namely stellar rotation. Why should stellar rotation impact what we see on a color magnitude diagram? Well, stellar rotation has a lot of impacts on the evolution of a star. First, it changes the hydrostatic equilibrium, which basically because, right, your pressure would be supported by the centrifugal forces. So you have another basically force counteracting gravity. So your cluster could live with a lower pressure, which means the temperature could go down. You could also have additional mixing in the inside of the star. And if you have a rotating star, that breaks its spherical symmetry. And what you can have then is what's called gravity darkening. For example, here's two ideas of how the surface temperature of a star would change in case it's fast rotating. And you see that the poles in this case would be the hottest regions, because they would be closest to the nucleus of the star, whereas these the bulge here at around the equatorial region would be the coldest, which is located at the largest distance from the nucleus. And if you take all these effects together, as shown in this paper by Bastian and Mink in 2019, then you can actually obtain photometric spreads that are very similar, for example, to the ones that we observed in NGC 1846. And then the question is, well, can we actually observe stellar rotation in these star clusters? In order to do this, we usually need spectroscopy, because the way we would measure stellar rotation is by the line broadening. So if you have a fast rotating star, basically all your lines would be strongly Doppler broadened, because the light coming from different sides of the star would have different velocities. So the line broadening gives us a term that's usually referred to as V sin I, because that's basically the equatorial velocity with which the star rotates, corrected by its inclination. And we can use the same spectral lines then also to search for binary stars, because binary stars then would reveal their binary status by line of sight velocity variations. The problem is that these clusters are distant and dense, so we really need to do crowded field spectroscopy here. And because they're distant and the stars are faint, we need an 8-meter class telescope. So I think the integral field spectrum of MUSE at the VLT has really been a game changer for our abilities to study these star clusters. For those of you who don't know MUSE, here's kind of MUSE in a nutshell. This is how it looks at UT4 at the Paranal Observatory. So it's composed of 24 integral field units, and you have two modes: a wide field mode that's basically seeing limited, gives you a 1x1 arc-minute field of view, and a narrow field mode with an AO improved 7.5 by 7.5 arc-second field of view. You have a medium wavelength resolution of around 2 to 3000 over a large wavelength range, basically covering all the optical wavelength range here. But the nice thing really for these kind of studies is that in both of the two modes, it gives us basically 300 by 300 spectra. And we've used MUSE quite extensively to study massive star clusters. For example, Sylvia has also used it to look at more but older star clusters in the Magellanic Clouds in search for the evidence of multiple populations. What I want to talk to you about is basically the beginning of the age range here. So we observed with MUSE a sample of young massive star clusters up to an age of a bit less than 2 billion years in the Magellanic Clouds. And here you see kind of the MUSE observations that we got of those 6 clusters. And in the following, I want to present some of the results that we obtained from the analysis of these data sets. Now, because I'm at Marseille and I know a lot of people here care about adaptive optics, I thought I should spend one slide at least to talk a bit about adaptive optics, because it's really key here. So this is one of the first observations that we got with the wide field mode adaptive optics supported MUSE capabilities. And here you basically have how the same field looked without and with the adaptive optics enabled. And actually this corresponds to a decrease in the full width half maximum of about 25%, which doesn't sound like much, but it actually allowed us to resolve 50% more stars in this image. And going to the more extreme, we also have dedicated narrow field mode data available for some of the star clusters, which gives us HST-like spatial resolution. And here you see this is one of the older clusters in the sample, NGC 1916. This is how it looked like with the wide field mode. And then the narrow field mode could really allow us to resolve this blob that you see here in the middle. And we really benefited from the work that has been done at this institute, because in order to analyze these images, we used a Mao IPSF model that was developed by Romain and others in-house. So you really made our life quite a lot easier here. Thanks for that. So let me go back to the analysis of the data then. So how we usually do this is that for each of the stars that you see in this data cube, what we do is we try an optimal extraction of the stellar spectrum. So we use a PSF model like MAUPI and HST astrometry, which usually exists for all of these fields. And then we try and deblend the spectrum of every star from this data cube using a software Pamplemousse that I wrote during the early days of my career in astronomy. And if this works, then we get nice spectra for all of the stars. So here you see two examples. And what you can already see that the star highlighted in red here has much broader spectral lines. And if we perform a full spectrum fitting using a code SPECSI that has been developed by my colleague Tim Oliver Bussert, then we can get also the B sin I measurements. And you see that indeed the red star is rotating much faster than the blue star here. Now, SPECSI doesn't only allow us to get V sin I, but also the line of sight velocity measurements, and also abundances and effective temperatures and some other properties. But in my talk, I really focus on the velocities and the broadening. So if we look at the broadening for all of the stars in our sample, then we really see that across this extended main sequence turnoff of NGC 1846, we really see a clear correlation between color and projected rotation velocity. And if we look a bit more careful, then we actually see that it's not really continuous distribution, but there's two quite distinct peaks. So also in these clusters, we have two kind of distinct populations. One is fast rotating and the other is slow rotating. Now with MUSE, we can actually then also go down to the bottom of the extended main sequence turnoff. And what we find there is that the fast rotators disappear. And this can also be explained because what happens here is we go down in stellar mass, and at a mass of about 1.4 solar masses or so, we're hitting what's called the Kraft break. So the stars below this threshold, they have convective envelopes, and stars with convective envelopes are quite efficiently braked by their stellar winds and the magnetic fields. So it's likely that basically all the stars in this spin, for example, would have been braked during their evolution, even if they were fast rotating at some point. Going to the younger clusters, we could then also study the behavior of V sin I across the split main sequence. And there we find a really consistent picture that stars bluewards of the split are always dominated by slow rotators, and redwards of the split, we mainly find fast rotators. So this is for NGC 1850 at 100 million years. Then this is at 200 million years, NGC 1866, and 300 million years, NGC 1856. So we always find the same. Blue stars are rotating slowly, redder stars are rotating much faster. Now, the nice thing of having basically this H sequence here is that we can then look at the evolution of stellar rotation at a fixed mass, but at different ages. And if we do this, then we can do two things. First, because we have such large stellar samples, we can also then basically perform a statistical inclination correction. So for example, this for the two older clusters here, these are all the V sin I measurements that we got for the red main sequence. You see this tail here towards low velocity. That's probably caused by stars with an inclination around 0. And if we apply a simple model here, then what we find is that the mean equatorial rotation velocity in these two clusters is around 300 kilometers per second. It's much smaller for the blue main sequence, but then we're really limited by the spectral resolution of MUSE, so we can just say it's slower than 100 kilometers per second, but we don't have the exact value there. But actually, just using the fast rotating stars, we can then see what happens to the stars as they evolve along the main sequence. So here's our two measurements of the mean rotation velocity. And what stellar models, like in this case, I use cyclist models developed in Geneva, tell us is that basically along the main sequence, the rotation velocity of a star shouldn't change. And only when it hits the main sequence turnoff here, the rotational velocity will drop. What's interesting is that these models also predict that because as the star evolves along the main sequence, its core contracts and its shell expands. you expect a drop in the critical velocity. So the critical velocity is the maximum velocity that a star can rotate with before it basically starts falling apart because of the centrifugal forces. And if we take the ratio of the two, then we see that actually as the stars evolve towards the main sequence turn-off, they'll be rotating quite close to their critical velocity. And if stars are rotating very close to their critical velocities, then they form what's called decretion disks. So basically they're rotating so fast that they start losing material around the equatorial regions. And these disks that are formed by this process are ionized by the radiation of the star and are then visible as line emissions, in particular in the H-alpha line. And these are then called either, depending on the spectral type, AE, BE, or OE stars. And actually, we find hundreds of these BE stars, which is the main spectral type at the turn-off of our clusters. We find hundreds of them really in the MUSE data. So what's shown here is our two clusters using basically spectral lines from available in the MUSE spectral range. And in particular here, the red dots are basically, so red here is H-alpha. And all the red dots here are stars that have H-alpha in emission. And you see that there's really a lot of them in both clusters. They're a bit less hard to, a bit more difficult to see here. But basically, if we look at where those stars are, then you see that we really have a lot of them in both clusters. What you can also nicely see here is that they're really confined to the red part of the main sequence. And that makes sense because here we have the slow rotators that shouldn't be BE stars. What's also interesting, if we look at a fixed magnitude here, 19, for example, we see that the younger cluster doesn't have any stars that show the BE phenomenon below this magnitude. But actually the older cluster does have quite a few there. And what we think happened here is that basically in the 100 mega years of evolution between those two clusters, those stars down here switched on the BE because they came closer to their critical rotation velocity as evolution continued. And this is also what we see if we plot the fraction of BE stars as a function of absolute magnitude. And here we have two clusters basically going from young to old. And we basically see that this peak shifts to smaller, to fainter absolute magnitudes here. But what you also see here is that these fractions of BE stars that we really get at the turn-off is surprisingly high, of the order of 60% or so. So it seems that most of the fast rotators in our clusters actually become BE stars just before leaving the main sequence. Now, this is interesting because BE stars were commonly assumed to be the result of binary interactions. So if you basically have a star accreting material from a closed binary, it will also spin up. And that can also give you a BE star. The relative importance of these two processes is still to some extent unknown, but I think this nicely shows that, yeah, the rotation velocities that we observe in these clusters might just be sufficient so that these stars turn off, become BE stars even without a binary companion. All right, to conclude this section, quickly, what causes the spin distributions? What causes this bimodality between slow and fast rotators? This is still to some extent unknown. So it has been suggested, for example, that tight binaries could slow the stars down. This is motivated by the observation in the field that if we look at the mean rotation velocity as a function of binary orbital period here, we see a drop if we go to periods below 500 solar masses. The origin of this drop is still unknown, but there might not be enough binaries in these clusters to actually form all of the slow rotators. Another idea would be that basically we have, while the star cluster is still embedded in gas, we have mergers, because these mergers would rejuvenate the blue stars, and then would explain these blue colors that we find for the slowly rotating stars. which are actually bluer than the predictions of stellar evolutionary models. Or something that we've proposed in a paper led by Sebastian would be that it depends on how long the protostellar disks live during the pre-main sequence. Because disks actually, when they couple to the star, they regulate angular momentum. So a star with a long-lived disk would basically be efficiently braked and would end up as a slow rotator. Whereas a star that lost its disk early on, for example, because of photoionization by a nearby O star, would be able to spin up to a much higher rotational velocity. So the answer of which of these three processes dominate, or if there's something else, is still out there. But towards the end of my talk, I now want to talk a bit more about binary stars. So binary stars, as you've seen in at least two of these three scenarios, may also play a role for stellar rotation, but they're also interesting in their own regards. But they're also very challenging to study because basically to study the binary stars, we need multi-epoch data to search for radial velocity variations. And then also for these young star clusters, where we only really have broad lines for our stellar spectra, radial velocities are really hard to measure accurately. So that's why the results mainly exist for one of the clusters now, NGC 1850, this 100 million year old cluster. And here you see color-coded in black are all the binary stars that we could identify in our sample. Which you can already see that there's an overabundance of binary stars in the kind of sparsely populated regions of the CMD. And this is where you actually expect binary interactions to push stars into. So what we typically find if we look at binary fractions in these young star clusters, which are the ones here, is that their binary fractions are higher than what we find in globular clusters. So in the evolved globular clusters, down here, we only find few percent of binary stars. In the young star clusters, those are much higher, of the order of 30 to 50%. This has probably two reasons. The first is that we look at higher primary stellar masses here if we go to the young clusters, but also that in these dynamic environments of the star clusters, binaries can be easily disrupted, for example, by passing single stars. And this is probably also one of the reasons why the binary fractions that we find in the field are still somewhat higher than what we observe in star clusters. So let's focus again on NGC 1850 here. And as I've already told you, that most of the binaries are actually found kind of off the main isochrone track that we expect for the single stars in this cluster. A former postdoc in Liverpool, Sara Saracino, who's now in Florence, she actually then went one step further and tried to constrain the periods of the binaries. So the periods is what we actually need in order to characterize these binaries properly. But this is very challenging because we only have few data points. Here you see all of our MUSE observations together with some archival ones. And then we have an infinite possibility of binary periods. And for example, for this star, which I think is this one up here, you see that there's basically two orbital periods that we could fit to it. Nevertheless, Sarah managed to find the periods and also measure the velocity semi-amplitudes for quite a few binaries in the star cluster. And now the most interesting ones are the ones with high velocity amplitudes and long periods. Because if you have a long period but a large radial velocity variation, the companion that creates those must be very massive. And in particular, this blue shaded area here is a region where the secondary star that we don't see must be more massive than the primary star that we see. And if you have something more massive that you don't see, it could be a black hole, for example. That's actually, as I'll show you in one particular example, not that easy. So let's have a closer look at one of those stars from this high period, high velocity amplitude sample. And this is this one, NGC 1850 black hole 1, which sits right on the, which actually surprisingly sits right on the main sequence turnoff. So you would think that this is just a normal main sequence star, and a main sequence star at 100 million years old has a mass of about 4.5 solar masses. And if you have something, and the nice thing about this object is that we don't only have the radial velocity variations that you see here. So you see it varies between 100 and 400, so really high amplitude. But we also have, from Ogle, we have light curves. And those tell us that the star is basically deformed by whatever it's moving around. This also allows us to measure the inclination. And if we correct for inclination and assume a mass of around 4.5 solar mass for our observed star, we find that it must orbit a black hole with a mass of 11 solar masses. Interestingly, that's not the only possibility, because what was proposed was that instead of this scenario, you have a black hole orbiting a main sequence B-type star, you can also have a real post-interaction binary where you have a bloated and stripped star, I'll come to what this is in a second, orbiting a stellar companion that's rotating very fast, and because it's rotating very fast, it's difficult to see its lines, and that's maybe the reason why we didn't detect it. But how can we tell? One good method in order to do this is what's called spectral disentangling. So let's assume that you have an observed spectrum that shows all kinds of crazy variations. What you do with spectral disentangling is you assume that you have two luminous stars moving on opposite sides of the orbit. So they always basically move in counterphase. And then you can actually try and infer whether there's two stars contributing to your spectrum. And the problem is here that actually the resolution of MUSE is not quite high enough in order to do this. So we asked for follow-up observations of this object with Flames Argus. And here you see our observation. Here's the star in question. You see it has quite some bright neighbors, but because we have an IFU, we're still able to deblend their contributions. And the nice thing here is we have bluer spectra, so we have more spectral lines, and we also have a higher spectral resolution. But of course, Flames Argus provides much less spatial information than MUSE. So we can really only target one star at a time with this instrument. And then my current postdoc, Reese Seeberger, he then applied this spectral disentangling and to the Flames data, and he could actually find two components here. So, and you actually see that it has worked because for the star that we know existed, for example, we observed this narrow line here, which is a magnesium line, which is not visible in the companion spectrum, but instead this has a helium line here. And the helium line is much broader. And this tells us two things. Is first, there is a companion that's luminous, that's very hot because it has helium lines, about 18,000 Kelvin, and it's fast rotating because of the line widths. But what we also found was that it was barely moving over the orbit. Whereas our known star is much cooler, 11,000 Kelvin, is a very slow rotator. We could only give an upper limit of the order of 50 kilometers per second, and has a huge orbital amplitude of 180 kilometers. Now, how can we explain this? So what we think happened here is we initially had a binary of two main sequence stars close to the turnoff. Then one of them evolved off the main sequence, started to expand, become a red giant, and this triggered then mass transfer to our companion star. The mass transfer caused the companion star to spin up. And basically, in this case, we had a quite significant mass transfer. So basically, at some point, we were basically left with a naked core of our star that we observed. The mass transfer stopped. But because the star had lost so much mass, it was in what's called a bloated state. So it wasn't yet in a new hydrostatic equilibrium. And so we have these two stars, and their combination actually gives us something that sits right on the main sequence turnoff. And this is the state in which the system is now. And very soon, actually, this star will contract and become a hot stripped star or a subdwarf O star that will sit bluewards of the main sequence somewhere down the main sequence. So, and we only caught it in this very brief phase of the evolution. But actually, there's some problem here because what's also interesting, as I said before, right, this companion does barely move. which means it must be 10 times as massive, at least, as the star that we initially observed. And this actually gives us a problem because basically this is quite a complicated plot, but it's also the last one I show. Afterwards, I'll conclude more or less. So bear with me for a second. So what we have here is the mass ratio between the two. And here's the period. And basically, a minimum period would be around 1 solar mass before these stars would actually touch. And what we basically expect is that when mass is transferred, the period widens because some mass is lost. So what you have here, so this is where we are now. And because some mass transfer has happened, basically, in earlier stages of the evolution, the period must have been tighter than the 6 days that we observe now. But actually, and then by how much it was tighter depends on the mass transfer efficiency. And this can take values between 0 and 1. But basically, you see that for all of these values, we would have the stars head in contact at the previous evolutionary stage. So we still don't know how to explain this, and that's what we still need to figure out. So maybe the prescriptions for mass transfer don't just work for this system. All right, so this is, yes, this is basically one star that we looked at now. There's a ton of other interesting stars, like also these stars here are also interesting potential black hole companions. They have very weird spectra, as you see here for one example. And we have flames data that we're now analyzing to try and also make sense of these stars. But this is really a bit of a tedious effort because you need follow-up observations of all these stars. And it's actually then that makes it very challenging to study large samples, especially also considering the oversubscription at the VLT, especially with MUSE. So that's why I want to conclude with an advertisement of one project I recently got involved with, the Wide Field Spectroscopic Telescope, a proposed 12-meter telescope purely for spectroscopy, which would have 144 IFUs and of the order of 30,000 multi-object spectrograph targets. And just to give you an idea, so this is what we could do with this telescope for a star cluster. So we would basically be able to cover almost the entire central region in one shot with such a telescope. And then because it's a dedicated experiment for one, well, basically one survey, it would also be much easier to get a good cadence for binary studies. So that was my advertisement, and then I'll leave you with my take-home messages that I think the color magnitude diagrams of young star clusters are mainly shaped by stellar rotation and binary interactions. While we made some progress, we still need to answer what sets the stellar spins and how many black holes do actually reside in these star clusters. And with that, I thank you for your attention, and I'm happy to take any questions.
Thanks a lot, Sebastian, for the presentation. Is there any question in the audience? Yes?
Thank you for this very nice talk. Can you explain this dispersion here you have on both sides of the main sequence?
So you mean in the presentation?
Yes.
So yeah, so the dispersion in color or the dispersion?
The dispersion color. Yeah.
Yes, it's I mean it's really surprising that it's so large there because all these stars, especially for the slow rotators. So I think one contributing factor is that stellar rotation also changes to some extent the main sequence lifetime of a star. Because your effective temperature changes, and because you can have additional mixing. So what you actually then expect is that when stars leave the main sequence, you would basically, instead of your effects would be the largest kind of. So I think what we just see here is that we we don't have two. I mean, we don't have a strict bimodality between two v sine I, between two rotation values, but we actually have a range, and this range then gives us a lot of different main sequence terms. So I think that's one part of the explanation. And then what I didn't mention in my talk, but which is also relevant, is that we actually have some slow rotators here. And actually what causes them is completely unclear at the moment.
Yeah, that was my point. Yeah.
So there's what we found in other clusters is that there's what's called UV dim stars. So these stars also appear to be dim in their UV colors, which may be linked to their rotation, maybe not. That's still debated.
Yes.
I have a question related to the metallicity, because we know that different isotopes can change or looks in this diagram between the metallicity. And if you have low ion rotation, you know that also that affects the type of metals that we can find in the star. Did you find a correlation between those two populations and the metallicity?
So yes, that's a good point. We didn't find a difference in the overall metallicity of the two populations. One thing that would be very interesting to look at, but where MUSE may be a bit limited, is to look at some elements that are particularly affected by rotation. Like I think like nitrogen, oxygen, potentially carbon. But yeah, we don't really have spectral lines, unfortunately, for them in the MUSE spectral range. So yeah, we didn't find any differences on the main sequence yet. There was a study by another group. I think they looked at the giants, and they found some variety in the giants that could be explained by differences in rotation.
Yeah.
In the V sine I measurements, the important part is the V. The sine I is
yeah, that's the sine I is more of a nuisance factor. So it's because yeah, we never really know how, what's the orientation of the star towards us. So a slow rotator could just be a fast rotator that we happen to see pole on. So the advantage that we have with MUSE is that if we have samples of hundreds of stars, we can basically make a statistical correction for sine I, saying that the average sine I think, should be pi over 4, I think. So
and in a globular cluster, you expect the sine I to be similar, or there's a random distribution of orientations?
So in a globular cluster, you would also then the distribute. So the orientation distribution should be the same. Just what we have in the globular clusters is that our stars are much less massive. So they have convective envelopes. So they're below this Kraft break. So even if my theory would be that at some point early in their evolution, they showed the same distribution, but the stars that basically were massive enough to maintain their rotation for a long time, they've all long gone. So now we're just left with slow rotators.
I have a question, perhaps a bit broad, but could you talk about how globular clusters are affected by the environment in which they're placed in? I mean, where they're positioned within the galaxy and other things. Yeah.
Yes, yeah, that's a good point. There's something which is discussed in the community under this horrible name of infant mortality. That actually a lot of globular clusters are expected to be destroyed just after being born, because kind of what what's the best way to destroy even a massive globular cluster is if it hits a dense gas cloud, say another molecular cloud or so. Because then that creates so much ram pressure that it would easily disturb the gravitational potential of the cluster enough. So actually, it's basically if you form, and you usually form stars, right? I mean, most of your gas is usually where most of your stars are. So kind of one theory why so many globular clusters survive is right. They formed in the turbulent environment of the early galaxy, and then were by mergers from other galaxies were ejected to basically safety in the halos. So, but yeah, in general, if your cluster forms close to the disk, it's more likely that it will get destroyed early on.
So you find an abundance of globular clusters outside of the galaxy, like in the outer regions of the galaxy.
Yeah, so for the Milky Way, we find a lot of globular clusters that are outside of the disk. There's a lot in the bulge region. There's a lot in the halo, and they're usually on rather inclined orbits. And actually, what we then observe is that every time a globular cluster is on its orbit passes through the galactic disk, that actually leads to enhanced mass loss.
Any other question for Sebastian?
So I might have one. Would it be interesting? So you use the MAOP to get the PSF, fit the PSF across your measurement. It would be interesting for your science to play a deconvolution algorithm to recover more high spatial frequencies, or it's not critical? Would it be possible and would it be interesting?
Yeah, so I haven't experimented much with deconvolution techniques. One thing I was always, when I started with this business, I was always told that deconvolution is tricky once you have finite signal to noise and might lead to artifacts in low signal to noise cases. I don't know whether that has improved by now, but I think yes, if you have a very good model for the PSF, then doing something like this would be a very interesting test. But I haven't done it myself.
But so if it was possible, it would improve your science. Like the angular resolution is critical for what you are presenting.
Yes. So I mean, yes, the main problem here is really the blending of nearby stars. And the better the spatial resolution, the more efficiently we can disentangle the different stellar components. We think that with knowing the PSF, if we use it to basically kind of fit all the stellar, all the contributions, we're already doing a decent job. But yeah, it would be interesting to see how that compares to some deblending problems.
And so I had another question is, so when you showed the thing with the two spectra moving, trying from one moving spectra to extract. So this I didn't grasp really how it was working, because it seems that you have like one data and two unknowns. So I didn't get how you were able to do this.
Yes, so I mean, the idea here would be that we observe. I mean, this is not what we observe, right? But we would basically observe different snapshots from this animation. And then the idea is that basically, our two spectra that we use to try and reproduce this, they stay the same. All that changes is their velocities. Okay. So basically, it's to some extent it's only two free parameters that we change here to fit the different observed spectra.
And you can make the assumption that the two companions have the same spectra. This is not too much of an assumption.
So the two companions don't need to have the same spectra. Just from one observation to the next, the spectrum of each star shouldn't change. And then another constraint would be that if one moves forward, the other moves backwards. Yeah. So because we know that if one's moving towards us, then for a binary, yeah. So I mean, to me, this is also somewhat magic.
Maybe because the the double star is not resolved. So you see only one spectra.
Yes,
So that's
yeah,
show it's an
indeed.
snapshot of the first image. So how could you know the shape of the orange and the blue shape? Like could you know, okay, there is this spectra, and there, I know that they are mixing.
Yes. So basically, if I go to this, well, basically what we would see, right? Because for example, this line only appears in the spectrum of one star, whereas this line only appears in the spectrum of the other star. So what we would basically see is in our spectra, we would see if this line has moved here, this line would have moved there. And then basically we can do this for every wavelength point to some extent, and then say, okay, this line only has a contribution from the one star, and this line only has a contribution from the other star. All right. So basically, in the hybrid spectrum, we would basically see the distance in wavelength space between those two lines change, and then you can use that information somehow magically to get two spectra out. So.
Thank you.
Which orbital time can you reach with these techniques, you guess?
So it's so I think it's limited to something. We need orbital velocities of the order of 20 kilometers per second or higher. So I would say that of the order of a few hundred days, it's still possible. And then probably if you have higher spectral resolution, it's possible even for wider orbits.
Okay, any other question? Also, it's we can thank Sebastian.
Oh no, I can ask you because it's a more of a curiosity for like features. Over lunch.
Yeah, very good.
Thank you. Yes.
I just want to find so maybe